We're continuing our discussion of limits. I just want to point out that the limit of a function is not actually related to the function value. Here f of 2 equals 1 because of this point I just circled. But that doesn't tell us anything about the limit of f as x approaches 2. The limit is based on the y value my function approaches as I come towards x equals 2, either from the left or the right, or both. And you can see that that in both cases is 2. We'll continue on here. Limits. So how can you actually evaluate a limit? You can check in your book for properties of limits that will help you evaluate them. And the good news is that a lot of the time, what we can do to evaluate a limit is simply plug in, so we'll substitute in x value we're trying to approach into the function and see what the y value does. Here's two examples from your book. This is example 4a. This is from page 63. So here, I'll use the whiteboard. If I want the limit as x approaches 3 of x squared times 2 minus x, I'm just going to take that value, x equals 3, and plug it in. So now I'm going to replace that x with 3, replace that x with 3. I can try to evaluate this expression, and it turns out I'm able to. I can evaluate that to -9. Nothing bad happened. I didn't have to divide by 0. If that works, -9 is my limit. There was no problem here. This is the easy case. So check out the next example. I want the limit as x approaches 2 of x squared plus 2x plus 4 over x plus 2. I can try replacing all those x's by 2. If I'm able to evaluate, here you can see I get 12 over 4, which equals 3. There was no problem, and the limit is 3. As you might have guessed, sometimes there is a problem. The most common problem is I'll end up having to divide by 0. We can still study these limits, and we're going to learn lots of algebra ways to get around the divide by 0 problem. You can see, I want you to look at example 5 now, see how it uses the product property for limits to get over this problem. So hit pause, check out example 5 right now, and then restart, please. You can look in your textbook at figures 2.2, 2.3, and 2.4. They're all examples of functions that, at some place, at least one x value, their limit fails to exist. There are 3 ways a limit could fail to exist. So I'm going to think about a particular x value, let's call it x equals c. A function could have no limit at x equals c if, when I approach c from the left, I get one value, and I approach c from the right, I get another value. That's what you see happening in figure 2.4, the integer function. The second way a limit could fail to exist is if the function approaches infinity or negative infinity as the x value approaches c. So we say it would increase or decrease without bound. I think that's example 2.3 and 2.2. You can see the function approaching infinity instead of some specific y value that you could name. The third way that a limit could fail to exist is if the limit actually bounces back and forth between 2 values. That happens very rarely. I don't need you to worry about that case happening in calculus AB or even in BC. So we said a second ago that one way a limit could fail to exist is if the function approaches one y value from the left and a different y value from the right. Well, it turns out to be such an important phenomenon to explore in calculus that we have a notation for it. So here's an example, and you can see how I use the notation. It's written in here below. So if I were to trace along my function, let me use a different color, trace along my function from the right-hand side, from the positive values, it looks like the y value I'm going to approach at x equals c is L. This is the notation I use. I say the limit as x approaches c from the right. That little plus sign up there means I'm approaching from the right. The limit as x approaches c from the right of f of x equals L. What if I approach from the left? It looks like my y value is approaching k. So I say the limit as x approaches c from the left of f of x equals k. It's my notation for one-sided limits. Your job now is to look up theorem 3 in your book, find out the important parts, and write theorem 3 into your notes.